and welcome to T Academy. In today's lecture, we'll start our discussion on feedback amplifiers. We have already looked at voltage amplifiers and current amplifiers. We have seen the considerations for input impedance and output impedance. Today we'll look at the different elements that we need in order to make a feedback amplifier system. So we'll start with the elements that we already know. We looked at source. So in case of a voltage amplifier, we represent the source by means of a Thevenin's equivalent, which means that we have a voltage source in series with the source resistance Rs. And we've already looked at load, which is typically represented by a resistance RL, and we saw the basic configurations of amplifiers, namely the voltage amplifier and the current amplifier. So in this block diagram, I am representing this amplifier as a voltage amplifier. So if you recall from my previous lecture, we have an input impedance, and the voltage across the input impedance is Vi, and we have a voltage dependent voltage source AV times Vi in series with the output impedance R0, and this is then connected to the load resistance RL, and we get the output voltage V0 across RL. But we are interested in making a feedback amplifier out of this basic amplifier configuration. We'll look at the benefits of feedback in a different lecture. Today I want to show how the complete block diagram looks like. So instead of connecting the output of the basic amplifier directly to the load, we insert in between what is known as a sampling network. So the output of the basic amplifier is connected to this sampling network, and then the sampling network's output is connected to the load, and the sampling network essentially samples a part of the amplifier output signal and gives it to a feedback network which has a reverse transmission gain beta. So the basic amplifier has a forward transmission gain A, which in case of a voltage amplifier is represented as A subscript V. And when we have feedback, then we also have a reverse transmission gain represented by beta. And the output of this feedback network is given to a mixer network. So mixer network, as implied by its name, it essentially mixes the sampled output signal with the input in order to give a new output signal at the input of the amplifier. So let's label some of the voltages and currents that we have. Voltage at the input of the basic amplifier is represented by Vi, and the current going into the amplifier network is represented by II, while the output of the basic amplifier, which is also the input of the sampling network, is represented by V, and the current going into the sampling network is represented by I. The load voltage, let's call it V0, and the current flowing into the load resistance as I0. So this is what the sampling network essentially samples. So a part of this output signal is then fed back to this feedback network, and the output of this feedback network, let's call it VF, and the feedback current, it can flow in either direction depending on how the feedback network is connected. Let's call it IF. So this gives a brief overview of the feedback amplifier block diagram. So we already know source, basic amplifier configurations, and load. Now let's take a deeper look at the new elements that I have introduced, namely the sampling network, feedback network, and the mixer network in a little more detail. So there are two ways by which we can sample the output signal. Let's say we have the basic amplifier with its forward gain A, which is connected to an output load resistance of RL, and we wish to connect a feedback network with a reverse transmission gain beta. Now if I'm interested in voltage sampling, that is, I want to sample a part of this output voltage, then this feedback network will be connected in shunt across the load. If this is the output, then the feedback network will be connected in shunt across the output. Therefore, this type of sampling is also known as shunt connection. So this is the current I0 and the voltage V0. Now similarly, we can also do current sampling, which means we are interested in getting a part of the output current. So in this case, we have to connect the feedback network beta in series with the load, like this. In this way, we are sampling a part of the output current, and then the feedback network can give it back to the mixer network. So these were two ways of sampling the output. Next, we look at the feedback network. So the feedback network is usually a combination of resistors. So if we have an output voltage, let's say of a buck converter, I've already explained this in one of my lectures on power electronics, which you can click in the link and watch it. So the output of the buck converter looks something like this. We have an LC filter in parallel with a resistance R0, and there we use a resistor divider network for voltage sampling. There are two resistors making a divider across the output, and we sample the voltage. Let's call this voltage VF, and the actual output signal as V0. So in this case, the reverse transmission factor beta is simply the voltage divider R2 over R1 plus R2. This beta always lies between 0 and 1. Lastly, we take a look at the mixer network. Just like the sampling network, where we can connect the feedback system in shunt or in series, we can do the same with the mixer network. So assuming that this is the basic amplifier network and this is the feedback network, if I want to do series feedback, then the source will be represented as a Thevenin's equivalent with the voltage source in series with a resistance Rs. And for series feedback, the feedback network is connected like this. So now the input voltage Vi also takes into account the sampled voltage, which can be either added or subtracted. So for the case of the buck converter feedback control, which I covered in my previous lecture, it was negative feedback, so the feedback voltage was subtracted from the input voltage in order to give the new input voltage. So this was series feedback. We can also do shunt feedback, but in this case we need to represent the source as a Norton's equivalent. So an ideal current source in parallel with the source resistance Rs. The feedback network is connected in shunt across the source. So that's it for today's lecture. I hope the feedback amplifier block diagram is clear to you. We took a look at the sampling network, feedback, and the mixer network, and how we can connect them in shunt or in series. In the next lecture, we'll look at the different type of gains which are associated with the feedback amplifier network. Thank you for attention and see you in the next lecture. Bye. The source as a Norton's equivalent. So an